lecture, problem session 9. Our problems today will be concerned with realizability theory, Harvard's polynomials and positive real functions. The first problem, 10.1. We will do some of them. 10.1a, let us say, where P of s is equal to s cubed plus s squared plus twice s plus 2. If I do this blindly, we have to form the ratio of n by m, because the odd power, what we have to do is to test the polynomial for Harvard's property. Odd, the degree is odd, so we take the odd part to the even part, which is s cubed plus twice s divided by s squared plus 2. So s cubed plus twice s cubed plus twice s. So this is premature termination, and the last divisor, premature because we expected 3 quotients. We have got only 1. The last quotient therefore must be a factor of both the even part and the odd part. In other words, s square plus 2 must be a factor of P of s. So we divide, although it is obvious, we carry out the procedure s cubed plus 2s and s square plus 2, so plus 1 s square plus 2. This is not a continued fraction expansion, this is a simple division, and therefore our P of s is therefore equal to s square plus 2 multiplied by s plus 1, and obviously this is a Harvard's polynomial. Its roots are obvious. One is at minus 1 and there are 2 on the j omega axis, plus minus j root 2. We skip b, then look at c. Can anyone tell me by looking at b whether it is Harvard's or not? Because there is a missing term. Okay. C is a purely odd polynomial, and therefore we have to use P prime s. P of s is s to the 7 plus s to the 5 plus s cubed plus s this is a purely odd polynomial. There is a slight simplification that is possible. We have to test this for Harvard. So why don't we see that s is a factor which is permitted in a Harvard's polynomial. So call this s times P1 of s, where P1 obviously will be purely even. P1 would be s to the 6 plus s to the 4 plus s squared plus 1. Is that clear? I have discovered that there is a 0 at the origin. Since it is purely odd, there has to be a root at s equal to 0, which is perfectly alright for a Harvard's polynomial. So we will have to test only the rest of the polynomial P1, and since this is purely even, we take its first derivative. P1 prime s is become 6 s to the 5 plus 4 s cubed plus twice s, alright, and we have to now carry out the continued fraction expansion. So we do that. You see, what we have to do is s to the 6 plus s to the 4th plus s squared plus 1. Let us do some more tricks of the trade. What we have to divide is by 6s5 plus 4s cubed plus 2s. The Harvard's test is not disturbed if either the divisor or the dividend are multiplied by a positive constant. So we can change this to keep numbers small. We can divide by 2. Let us say this is 2 and this is 3. And again, to keep numbers small and manageable, we could divide this whole thing by 3, we could multiply this whole thing by 3. Okay, is that clear? Why we can do that? Because we want to keep our numbers nice numbers. All that we are concerned about is the sign of the coefficient of the quotient. So it does not change if I multiply or divide by a positive integer. Yes.
Affect the further variance that we are
we will simplify that also. If it does affect further division, we will simplify that also. We will multiply or divide by a positive constant.
No, sir.
Maybe it will
Like,
include some negative.
Yes?
So in this case, we are dividing by 2.
Right.
So instead if we, so that means we can only divide.
We can division and multiplication.
We can only extract the
Positive constant.
We cannot multiply.
Multiplication and division are the same operation.
No, sir. If we multiply, then maybe the quotient becomes more. Quotient may become negative.
No, you see,
Become negative.
just a minute. What we are doing is, we are making a continued fraction expansion of P1s by P1 prime s. What I am saying is, I could divide this by an arbitrary positive constant R1. I could multiply this by another arbitrary positive constant R2 without affecting the signs of the quotients. Is that clear? So it will not affect the signs of the coefficients of the quotients. All that it affects is the quotient,
So
the value of the quotient.
What I was saying that if we divide that S6 plus S4 by some value, we carry out the division, then further subtraction may introduce negative.
No, why should it? Because it will depend on the value of the quotient. It will not affect. You see, this is simply R1 by R2 multiplied by whatever the CFE is. But R1 by R2 is a positive number, so it will not affect. This we do to keep numbers small. If you are fussy, you go ahead with the original one. I have no objection. End up in 1/6, 1/35 and so on and so forth. Alright? Okay. So what we are doing is 3s to the 5 plus 2s cubed plus s, that divides 3s to the 6 plus 3s to the 4th plus 3s squared plus 3. So s is the quotient. I get 3s to the 6 plus 2s to the 4th plus s squared, and so the remainder is, for reasons that I have told you, simple reasons, I bring the remainder here. So I get s to the 4th plus 2s squared plus 3. The numbers are not too bad, so 3s to the 5 plus 2s cubed plus s. My quotient is 3s, so 3s to the 5 plus 6s cubed plus 9s, and the remainder is minus 4s cubed minus 8s, and I do not have to proceed further. As soon as I get a negative coefficient here, I know that the next quotient shall have to have negative coefficient, and therefore I conclude P of s is not Harvard's polynomial. Alright, we don't have to carry out, we don't have to complete it. As soon as you get a negative coefficient, you know that the job is done. We skip D, we look at E, or E is also purely odd. E is s to the 5 plus 2s cubed plus s. We don't differentiate this first. What we do is we simplify this by taking an s common, and I get s4 plus 2s squared plus 1. Do I have to carry out continued fraction? Isn't it obvious that this is s times s squared plus 1 whole square? Had I done the continued fraction expansion, what do you expect of this? There would have been premature termination. I would have got only one quotient. Anyway, you can do this. Therefore, this is Hurwitz. This is a Hurwitz polynomial. F I have already done in the class, so skip that. 10.2 says determine whether the following functions are PR. For the functions with the denominator already factored, perform a partial fraction expansion first. Alright, for example, A, the function is f of s equal to s squared plus 1 divided by s cubed plus 4s. It says determine whether this function is PR or not. For these functions with the denominator already factored, well, this is also approximately factored, because you know s is a factor, then s square plus 4. So, make a partial fraction expansion, s square plus 1 s into s square plus 4. Now, in this partial fraction expansion f of s equal to s square plus 1 divided by s into s square plus 4. The partial fraction expansion do not bring in the complex poles, the imaginary poles. You make a partial fraction expansion in terms of s square plus 4 in the denominator. That is, you write, there is a pole at the origin, corresponding to this you write k0 by s, and corresponding to the next term, if the function is to be positive real, then the residue must be positive, must be real and positive, but we do not know what it is. So, we assume that the residue is, let us say, k1, twice k1 s divided by s square plus 4, some residue, okay. And you notice that k0, can you see what k0 is? No. No, k0 is not 1. 1 by 4. Because as s tends to 0, it is 1 by 4s. Okay. And what is k1? K1 is s square plus 1, multiply by this and divide by twice s. So, 2s squared with s squared equal to minus 4. Alright, that is k1. So, this is minus 4 plus 1, that is minus 3 and minus 8, which is equal to 3, 8, real and positive. Do I have to do anything else? Do I have to check the real part on the j omega axis? Okay, what we have done is we have discovered that there are poles on the j omega axis. We have verified that none of the poles are multiple, they are simple poles, and we have verified that the residues at the poles k0 and k1, they are real and positive. The next part should be the real part of f of j omega. Now, do we have to check that? Don't you see that the real part of f of j omega, what is the value? Yeah? Identically equal to 0, because this is a odd rational function. This is even divided by odd, so it is an odd rational function. At s equal to j omega, it is purely imaginary, so the real part is 0. In other words, the conclusion is that the function is positive real.
So, while doing the partial fraction expansion, so in the second term we should assume 2k1 as plus k2, some constant. We cannot directly assume it as to be positive real and assume k2 is equal to 0.
Can I? That is a good question. Why do we write 2k1s? Because, yes?
We got it this way because we take them separately, the two poles, and add such terms.
No, but there was a constant term.
So,
You recall that this was k1s minus k2 times omega 0, that is 2k2. So, in all fairness, you should have written this as 2k1s plus k2 and discovered that k2 equal to 0. It is a very good point, it should be done, because you do not know whether the function is PR or not.
Yes.
You have to find out k1 and k2. You can easily see that k2 is equal to 0 here. How do you see? There is no term of coefficient s. Does that satisfy everybody?
So we say when b is equal to 0, then we have
Do it the way you like. But what I say, it is a purely odd rational function, numerator is purely even. Now, by combining these two, if k2 is non-zero, we shall not get an even polynomial in the numerator. They are very simple common sense argument, alright. Therefore, k2 must be equal to 0. The next the next one that we take is, we will skip B and C, we will look at D. We will look at 10.2 D. The function is f of s equal to s square plus 4 divided by s cubed plus 3s square plus 3s plus 1. The denominator here is not factored. So we'll have to go we'll have to go step by step. First, it is obvious that f of s is real when s is real. First part is okay. Now to see whether it has right half plane poles or not, we must make a continued fraction expansion of s cubed plus 3s divided by 3s squared plus 1, right? We must check d of s, the denominator polynomial, whether it is Hurwitz or not, and for that we take the higher power term, that is the odd part, divide by the even part and find the continued fraction expansion. I have s by 3, I could have multiplied this by 3, I could have done that. Let us see, s by 3, so we get s cubed plus s by 3 this is 8 by 3s, is that clear? 3 times 3, 9 minus 1, okay, 8 by 3s, 3s square plus 1, so my quotient becomes 9 by 8s, 3s squared, 1, 8 by 3s, 8 by 3s, 8 by 3s, 0. The degree is 3 and I have got exactly 3 quotients, no premature termination, therefore no j omega axis poles and the denominator is indeed a Hurwitz polynomial, therefore it has no poles, the function has no poles in the right half plane. That part is okay. We don't have to check any residues.
So why don't you just take s plus 1 whole cube?
Oh, I could have done that also. If I had discovered it earlier, I would have done that. Okay. If it is s plus 1 whole cube, then there are multiple poles at s equal to minus 1. Does that violate the positive realness? No, not necessarily. You must check the real part. You see, what Mayank is saying, why couldn't you or someone else is saying, why couldn't you see that this is s squared plus 4 divided by s plus 1 whole cubed? Indeed it is, which means that there is a pole at minus 1 of multiplicity 3. Now does this violate positive realness? No, not necessarily. Multiple poles on the j omega axis are not allowed. Now because there are no multiple poles on the j omega axis does not guarantee that the function is PR. We still have to check. Okay, let us check. We check the real part now, that is real part of f of j omega. No, we don't write real part f of j omega, we write the polynomial a of x directly. A of x becomes 4 minus x from the numerator, then 1 minus 3x, then that's all, because n1 is equal to 0. The numerator odd part is equal to 0, and obviously this will not always be positive, obviously, isn't that right? It is positive only when both terms are positive or both terms are negative. That cannot be guaranteed. So not always. We don't have to check which range which range it is positive, which range it is negative. We don't have to find that out. As soon as we see there is a root on the positive real axis x equal to 4, there is a root at on the positive real axis at x equal to 1/3. Okay, so at 1/3 and 4, at both places the function changes sign, and therefore not always greater than equal to 0. Therefore f of s is non-PR. Is it okay? All right. We shall skip E also and go to 10.3 is simple. We have already discussed in the class. 10.4. Show that the product of two PR functions need not be PR. Show that the product of two PR functions need not be PR. F1, 2 are PR. You have to show that this is not necessarily PR. The first part, also show that the ratio of one PR function to another PR function, that is, let us say another function which is f1s divided by f2s, this is not necessarily PR. You have to show, and then give one example of each. Give one example of each. That is, give an example in which the product is not PR, although individually they are PR. The ratio is not PR, although individually they are PR. Okay, we'll prove. We'll show for this. For the other one, it should be absolutely clear. You see, what do you have to do? F1 and F2 are PR. All right. You have to show that the product is not necessarily PR. Now, as far as the first condition is concerned, in the definition, that is S real, f of s real, that is satisfied. So it is the second condition. And here you don't have to go to the j omega axis, because nothing is known about f1 and f2. You don't know whether they have poles on the j omega axis. You don't know whether, well, we know that they are, if they have poles on the j omega axis, they are simple. But these two poles may be coincident. All right, f1s may have a j omega axis pole at the same point as f2s. Then they will have a multiple pole at s equal to j omega. So this is one reason. But even if they don't, even if the product does not have a multiple pole, there is this real part consideration. That is, suppose real part of f of s, I am taking the complete S plane now, complete right half S plane. I don't have to go to the special case. It can be proved in a more general terms. Real part of f of s is the real part of the product of the two. So let's say one is u1 plus jx1 and the other is u2 plus jx2. All right. All that you know is u1 is greater than equal to 0 and u2 is greater than equal to 0. Why? Because f1 and f2 are PR. All right. So this is equal to u1 u2 minus x1 x2, which is not necessarily greater than equal to 0. It will depend on the value of x1 x2 as compared to u1 u2. All that we know is u1 u2 is positive, but x1 x2 may be positive and greater than u1 u2. So it is not necessarily, therefore f of s is not necessarily PR. Is the proof okay? Not necessarily, it could be. It could be PR also, but it is not necessarily PR because x1 x2 may be greater than u1 u2. Similarly, you can prove for g of s. But now an example. Give a simple example in which the product of two PRs is not PR. Give an example.
So both are 1 plus 2j. For example.
Both are 1 plus
2j.
1 plus 2.
J.
No. 1 plus 2j is not a positive real function. It is not a function of s.
1 plus
S
2.
plus 2s.
S plus
J.
S plus j is not PR. Okay, 1 plus 2s. And f2? Oh, same thing. Okay. How do you know this is not? How do you know this is not PR? Multiple pole at which location on the j omega axis? J omega axis is in ocean at infinity. But why did you have to go to 1 plus 2s? Why not simply s? Simply s and s. Okay. Now, give an example of f1 and f2 which are individually PR, but their ratio is not PR. Ratio f1 by f2. Simplest example.
S minus S.
That is right. The ratio is s squared, which is double poles at infinity. Yes.
In this question, can you straight away prove the example?
No.
The first.
This
If you
is-
have an example which is not PR, F1, F2, then it shows that.
Okay. All right. An engineer always goes by that kind of intuition. But when someone says prove, 10,000 examples are not enough to prove. But one counter example is enough to disprove. Okay? So if it is proved,
We have a counterexample.
This is a counterexample.
A counterexample is enough here? Why? Because it says not necessarily peer.
So then we can give two examples. One in which the product comes out to be a peer and the other not.
Wonderful. Because it is not necessarily peer. The proof is a qualified proof. So a counterexample shall do here. Alright? Okay, the next problem that we work out is we skip 10.5 and 10.6. Both of them is very interesting. We go to 10.7. No, we skip 10.7 also. Let's skip it for you. Or maybe there is a point in 10.7 which I want to illustrate. Okay, 10.7 says given z of s is equal to 2s square plus s plus 2 divided by s square plus s plus 1, it is given that this is PR. Okay, it is given that this is PR. Determine the minimum part of real part of z of j omega and synthesize z of s by first removing this minimum part. That is, synthesize z of s as minimum real z j omega plus z 1 of s, let us say. Let me tell you what this problem involves. It is given that this is PR. So you need not test whether it is PR or not. What it says is remove the minimum part of the real part of z of j omega. Now what would this be in terms of an element, network element? Resistance, because it's a real part, it's a real quantity. Remove the minimum value. Can you remove the minimum value? You can, without destroying the positive real character of the function. For example, if the real part of z of j omega, let us say it varies like this. It varies like this. Minimum real part of z of j omega has always to be positive. Okay? Always to be non-negative. Not positive, non-negative. Now the minimum value is somewhere here. Minimum is somewhere here. Let us say this minimum value is R1. If I form a function z of s minus R1, will this still be positive real? Yes, it shall still be remain positive real, because the minimum value of this shall now be 0. And therefore, what this problem says is, one of the ways of simplifying a function is to take out a constant from it. If you take it, what value of constant? That constant, he says, take the minimum value of the real part of z of j omega. If you do that, perhaps the function would be simpler. Let us see if we can do that. Our function is z of s equal to 2s squared plus s plus 2 divided by s squared plus s plus 1. So real part of z of j omega, I am not taking a of x now. Why not? Because we are not testing. We are not testing it for positive realness. I have to find out the minimum value of the real part of z of j omega, and therefore I have to find the total function. The total function would be m1 m2. m1 is 2 minus 2 omega squared. Do you see that I am putting s squared equal to minus omega squared immediately? Okay, this is m1, and m2 is 1 minus omega squared, then minus n1 n2, that is minus s squared, with s squared equal to minus omega squared. So this is plus omega squared. Is that okay? Is this okay what I have written here? Okay. The numerator should have been m1 m2 minus n1 n2, and the denominator is m2 squared minus n2 squared with s equal to j omega. Alright, this is the real part of z of j omega. Now m1 is 2 plus 2s squared, and s squared equal to, no, I don't want s equal to j omega, I want s squared equal to minus omega squared. Therefore, 2 minus 2 omega squared, m2 is 1 plus s squared and s squared equal to minus omega squared, so 1 minus omega squared, then minus n1 n2, so minus s multiplied by s, so minus s squared, which is equal to plus omega squared. Okay, and in the denominator I shall have 1 minus omega squared whole squared, then plus omega squared. So let us see what this function is, then you have to minimize this. So I get real part of z of j omega. In the denominator I get 1 minus omega squared plus omega to the 4th. Is it okay? 1 minus omega squared whole squared, so 2 omega squared plus omega squared. Okay, and in the numerator I get the constant will be 2, the 4th power will be twice omega to the 4th, then here it would be minus 2 minus 2, that should be minus 3 omega squared.
Plus minus 2.
Not minus 2. It will be minus 3 because, is that okay? Alright. So how do I find the minimum value of this? Is it obvious where the minimum is? Omega squared equal to 1. How do you know? How do I find the minimum value? Let us put omega squared equal to x squared. Then 2 minus 3x plus 2x squared divided by 1 minus x plus x squared.
So the above expression is equal to 1 plus 1 minus omega square whole square by 1 minus omega square plus omega square.
So 1 omega square will be 1 because if we divide the numerator and denominator by omega square and we group them as 2 into omega square plus 1 upon omega square, we get a similar term like.
We simplify, it comes out to be 1 plus 1 minus omega square whole square.
Which one? Numerator?
1, no, total term.
Total term becomes
1
plus
1 minus omega square
whole square
divided by 1 minus omega square whole square plus omega square.
Oh, that's wonderful.
And this is minimum at omega square is equal to 1.
Quite so. Is that clear? No, it's not very, he's very fast, very quick to see. I didn't see that so fast. I think he's right. You see, what he does is, he takes 1 minus omega squared plus omega 4 out from the numerator. So what you are left with is 1 minus 2 omega squared plus omega to the 4th. Is that okay? The numerator is denominator plus this, and therefore it is 1 plus, you see the numerator 1 minus omega square whole square. Yeah, there is no trick. It's a very simple observation. But if you do not see it, then you do the usual thing, that is 2 minus 3x plus 2x square divided by 1 minus x plus x square. The minimum occurs when 1 minus x plus x square denominator multiplied by the differential coefficient of the numerator, which is minus 3 plus 4x, is equal to the denominator 2 minus 3x plus 2x square multiplied by the differential coefficient of the denominator, which is minus 1 plus 2x, and make your life miserable by simplifying this and finding that indeed x equal to 1 is the answer. You have to simplify this. Okay. Now, therefore, our sum and substance is that the minimum of real part of z of j omega is equal to 1, and I remove this, which means that my z1s would be equal to z of s 2s square plus s plus 2 divided by s square plus s plus 1 minus 1, that is equal to s square plus s plus 1. What am I left with? S square plus 1.
So what is the there are 2 minimums in this equation?
If there are 2 minimums, then obviously you have to take the global minimum, absolute minimum. You see, you can subtract this. No, you cannot, because then the remainder function will be non-pure, isn't it? So you can subtract only this much. You have to take the global minimum. It's a very correct question. There may be two minima. Then you have to check what is the value at this minimum, and you have to take the lowest of them. You have to take the lowest of them. Very correct question. Now in this particular problem, therefore I have z of s equal to 1 plus s square plus 1 divided by s square plus s plus 1, and the problem is that I have to synthesize this. I have to synthesize this. Now some tricks of the trade. What I have is z of s equal to 1 plus s square plus 1 divided by s square plus s plus 1, and one should be able to see that I can write this as
Divide by s.
1, no, I don't divide by s, I divide by s square plus 1. So I get 1 plus s divided by s square plus 1, alright, which I can write as 1 plus 1 by 1 plus 1 over s plus 1 over s. Don't you see that I have expanded into a continued fraction, and I have done this by inspection. Now since this is an impedance function, this is impedance, this is admittance, this is impedance, this is admittance. Okay, so what is the network then? Am I going too fast?
Yes.
Okay. This function, I see that this term is there in the denominator also, s square plus 1. So I divide. There is no guarantee that this procedure is going to give you correct results in the general case, but here it is extremely simple. What I find is that 1 plus s remains, I have divided by s square plus 1, so s by s square plus 1. Then I treat this one, I divide by s, so I get 1 here, 1 s and 1 by s, which is exactly in the form of a continued fraction, and the network now shall be a 1 ohm resistor, an impedance, then an admittance of 1 ohm, which means another 1 ohm resistor. Then in parallel we have an impedance of 1 Henry and a capacitance of 1 farad. So this is my z of s, and the synthesis is complete. We have actually found a network because this function was simple. That's it. Okay.
If you would have gone about assuming that the function is like a single tune circuit, taking omega not equal to 1 and finding beta, then you could have.
No, which is not correct, because we have here a 1 ohm and a 1 ohm. We don't have a pure single tune circuit. It is not that we have a series LCR, no.
No sir, the second part, 1 plus s square.
Oh, the second part is okay. Second part is a parallel tuned circuit, isn't it? There is a resistance, then in parallel with it, it's not one of those circuits that we have dealt with earlier. No, it's not. You see, what we did was, we had a series tuned circuit in which R came in series with L. We had a parallel tuned circuit in which a capacitor came in parallel with a resistance and a inductor. It's none of them. We have to be
So
careful.
we removed one from the expression and then we have synthesized.
The rest, and then added one. This one was the one that was removed. What we did was, we wrote z of s as 1 plus something. So this is my z1. You have to bring it back. You removed only to facilitate handling the rest of it. Why did you remove? Because the function, the remainder function, becomes simpler than the original function. And that is the strategy. Given a complicated problem, you convert it into simple problem. Okay, my next problem is 10.8. 10.8 perform a continued fraction expansion of the given ratio y of s equal to s cubed plus 2s squared plus 3s plus 1 divided by s cubed plus s squared plus 2s plus 1. It says perform a continued fraction expansion on the ratio, what does the continued expansion imply if y of s is the driving point admittance of a passive network? What does it imply? Draw the network from the continued fraction. Okay, so let's do the continued fraction, then see what the implications are. The continued fraction is s cubed plus s squared plus twice s plus 1, s cubed plus 2s squared plus 3s plus 1. So you take 1. What is the dimension of this? This quotient? Admittance. So it is y. We must keep a track. I get s cubed plus s squared plus 2s plus 1. Now in continued fraction expansion, here, because we are going to realize a network, we are not permitted those liberties. Which liberties? Multiplying by positive constant. No, because that will change the network elements. We are not allowed that liberty. If it was simply to find out whether it's Hurwitz or not, then of course you do whatever you like. Okay, so my remainder is s squared plus s squared plus s. That's all. Then I get s cubed plus s squared plus 2s plus 1. So s is the quotient, s cubed plus s squared, and this s is now an impedance. I am left with 2s plus 1, s squared plus s by 2, s squared plus s by 2. This is an admittance. Why? Then I am left with s by 2. I am left with s by 2, and s by 2 divides 2s plus 1, 4s, 4s or 4? 4, simply 4. 2s, 1, and this is an impedance. 1 divides s by 2, s by 2, s by 2, 0. And this is an admittance. Now, if you look at the total continued fraction, I don't know if you can see it. Total continued fraction is that, no, let me do it this way. Yeah, okay. Can you see the whole thing on the screen?
Yes.
Yes, okay. The next question is, we have done the continued fraction expansion. What does it imply? What does it imply? What is the implication? If there are more than one implication, tell me so. Yes? One of the implications is, since all these quotients have positive coefficients, obviously it's realizable. Therefore, y of s is PR. Agreed? Any other conclusion that you can draw from the continued fraction expansion? Any other conclusion? Yes? About the nature of the network.
So, how can we say that y of s is PR?
How can you say that y of s is PR? Because the continued fraction expansion yields terms like 1, s, s by 2, 4, s by 2, which are resistors, inductors or capacitors. Right? Therefore it is PR. Therefore it is realizable. In fact, the network is obvious. I will draw the network in a moment. Network is obvious, but I want you to make another conclusion about the result that we have got. That it is not, it is an RLC network. As simple as that. It contains resistors, inductors as well as capacitors. Let's draw the network. What we see is that y of s is equal to 1 plus 1 over s plus 1 over s by 2 plus 1 over 4 plus 1 over s by 2, which means that the network would be 1 ohm resistor, the next one would be 1 Henry inductor, the next one would be a shunt element, half farad capacitor, next one would be a 4 ohm resistor, and finally half farad capacitor, and this is y of s. It's an RLC network, that's all that we you can say a few other things, that it's an equal capacitor network. Two capacitors are equal, resistors are not equal. But let me caution you, this is an oversimplified example. This cannot be used in general. In general, continued fraction. Yes.
The capacitor should be 2, sir.
Pardon me?
The capacitor.
No. This is an admittance. This is admittance, this is impedance, this is admittance, this is impedance, this is admittance. So it's a half farad capacitor. What I wanted to tell you is that this is not in general applicable. That is, continued fraction does not necessarily give you a realizable network or a realization. For example, none of you questioned me as to why I carry out a continued fraction expansion only starting with the highest powers. Why not lowest powers? What's wrong? If you do that here, you will see that after a few steps you get negative. That is also not general. There are situations where continued fraction with highest powers will give positive quotients. Continued fraction with lowest powers gives negative. There are situations where continued fraction with lowest powers works, that with the highest powers doesn't work.
So how do you do continuous fraction by lowest power?
How do you do? You write it in the reverse fashion. That is, start with the lowest power. You write this, instead of s cube plus s square plus 2s plus 1, you write 1 plus 2s plus s square plus s cube. Similarly here also 1 plus 3s plus 2s square plus s cube.
Quotients will be 1 upon s. You know that.
That's right. And 1 upon s, you know, if it's an impedance, then you know it's an inductor. If it's a capacitance, you know it's a capacitor. Okay. So coefficient continued fraction expansion at lowest powers does not work in this case. There is no general rule as to which one will work. Whether both will work or not, whether one will work or not, there is no general rule. This is a simple example, that's why it happened to be so. We shall end up this class with one more example from 10.9. And let's do B. 10.9 B. Just one more. It is given that this function is an impedance function, that is g of s equal to s plus 1 divided by s into s plus 2. Synthesize the impedances by successive removals of j omega axis poles or by removing minimum real part on the j omega axis. You have to synthesize this by successive removal of poles on the j omega axis. Well, as far as, or by taking the minimum value of the real part. As far as this is concerned, does it have a pole on the j omega axis?
No.
Yes or no?
Yes, sir.
Yes, it has. Where? At the origin. So you can write this as K0 by S plus some remainder impedance Z1S. What is K0?
1 by 2.
1 by 2. Therefore, Z1 is equal to S plus 1 S into S plus 2 minus 1 by 2S. Let's see what this is. 2S S plus 2, 2S plus 2 minus S minus 2.
So 1 by s, y so s plus 2.
So S and S cancel, this also cancels. What do we get? 1 by 2S plus 4. Is that okay? Have I made a mistake? Yes, I have. Therefore, I get z of s as equal to 1 by 2s plus 1 over 2s plus 4. Do I have to do anything else?
No.
No. So my z of s becomes first a 2 farad capacitor, all right, and then a parallel combination of
2 farad capacitor.
2 farad capacitor, no Henry. This is impedance, so the denominator is in
1 by 4
admittance,
ohm.
and 1 by 4 ohm. Okay. question, is there any other way you could do it? Just by looking at poles on the geometry axis. Is there any other way? Let's look at the function again. Could we do it in some other way, some other obvious way? Instead of z, suppose we took the y, reciprocal of this. Then what would we have got? Y of s would be equal to s into s plus 2 divided by s plus 1. Obviously this has a pole where? On the j omega axis. You see, you have to remove poles on the j omega axis only, no real axis. Now it has a pole at infinity, and what is the residue at infinity? 1. So it is simply s plus y1 of s. Okay. Now if you remove s from here, what is y1?
S by S plus
1 by s plus 1.
So it is s plus 1 by s plus 1. Is that clear? S square plus s. No, that doesn't sound right. S by s plus 1. Is that correct? S square plus s. Yes, that is correct. And now the network is also obvious. What we have is y of s equal to s. So I have a 1 farad capacitor. Then what?
so 1 ohm.
And
1 ohm
1 farad in series.
and 1 farad in series. Right. So at least there are two networks that we have found out immediately. Which one? Last question. If these are at your disposal, you know that the same function is realized by this as well as this. These are both RC networks, no inductance. Okay. Now, which one, if any, would you prefer? Why? Why? Smaller capacity. Larger the capacity, the price goes up. It's purely economic consideration, nothing else. 1/4 ohm resistance and 1 ohm resistance doesn't matter. Price will be, now I think it is about 50 paisa or 35 paisa. If you want a 1/4 watt resistance. It is, pardon me?
Losses in the lower network will be more.
Losses in this network will be more. Why?
Larger resistance.
But the total effect is the same. No, he has it. He has something. He has brought out a point. What you said is not correct. Losses in this will be less. Not less. Losses in the total shall be the same. But there is one more consideration besides cost. One more consideration for using lower valued capacitors. Can anyone tell me what this is? Pardon me? Size, yes, size of course is important. As the size increases, the cost also increases. But there is one more consideration, very obvious and very simple consideration. Larger the value of the capacitor, larger is the leakage or the impurity. Therefore, one shies away from large capacitors. Whether it is the power system laboratory or electronics laboratory, you should choose the lower value of capacitor. Lower the capacitance, lower are the losses. That's all for today.